Welcome, ladies and gentlemen, to our first lecture on fluids. The study of fluids, especially fluid dynamics, is a very complicated study, probably beyond the scope of this class. So what we're going to do is look at some very simplified cases and get a more general bird's eye view of fluids. So let's start by asking the most basic question here. What do we consider a fluid? A fluid is a substance that will flow or change the shape of the volume that it occupies. So for example, if I have a glass and it's filled with water, and we dump that glass out on the table, the volume that it occupies will change shape, right? This is a fluid, okay? This is our kind of most basic example. We always think of water when we think of fluids. And the shape of the water is dictated by the container that holds it in, right? By contrast, a solid will tend to maintain its shape, right? So if we had a ball in this glass, it looks like this. And if we take it out and set it on the table, it still looks like this, right? So a solid maintains its shape wherever it is, right? The shape of a solid is one of the properties of that object. And a fluid doesn't have a set shape, okay? The shape of water is not one of the properties of water. But fluids aren't only liquids, like water. The term also encompasses gases and plasmas. So the air that you breathe is a fluid. The helium that fills a balloon is a fluid, okay? In effect, we can kind of consider something a fluid if it's a macroscopic gathering of material and it's not a solid, okay? So our two main types of fluids are gases and liquids. And both of these things are made up of molecules that are bouncing around, okay? So let's consider water and steam. So we're even dealing with the same molecule, okay? So in water, we have an oxygen with some little hydrogens like this, right? This is an H2O molecule. This is what makes up water. And these molecules are close enough that there's some attractive force between them, okay? And they kind of stay close enough that there's always this attractive force between the molecules that make up the water. And we call this cohesion. In a gas like steam, these same molecules are further apart and moving much faster, so there's effectively no attractive forces between the molecules. They don't have cohesion, okay? This cohesion causes water to generally occupy a set volume. The shape of the mass of water will change based on whatever container we contain it, but the volume of water is always going to be basically the same, okay? Now, I say basically, water can technically be compressed by the tiniest amount if you really squeeze it, but for all effective purposes, liquids are not going to compress, okay? So the volume of water is always the same. So just for illustration purposes, let's say I have 6 equal cubes. And they're arranged like this when the water is in a glass, okay? The glass forces them into this arrangement. Then when the glass is spilled out on the table, I still have these 6 equal sized cubes, okay? So I still have the exact same volume, but then they arrange like this on the table. So the shape is dependent upon what the water's interacting with, the glass or the table or whatever else. But the volume of the water, the 6 cubes that I have, is always the same, okay? And if we wanted to make this even more realistic, maybe instead of the 6 equal sized cubes, when it's on the table, it turns into 12 cubes that are half the size, right? Something like that. But the volume is always going to stay the same with the water, okay? By contrast, if I have a set mass of steam in a space that's, say, this big, the steam will fill that space, okay? The steam will take up all of that space. But if I put that same mass of steam, that same exact mass, so the same exact number of molecules of steam in a space that's this big, it will fill this space, okay? the volume and the shape of the gas will change depending on its circumstances. So liquids and gases are both fluids, but the ability of gases to readily change their volume in addition to changing their shape constitutes a difference between the two. Okay? And this difference comes from this cohesion. Liquids have cohesion, the molecules are attracted to each other. Gases have molecules that are far enough apart and fast enough moving that they're not generally attracted to each other. So now I want to take a step to the side for a second and consider density. We've mentioned it briefly before, but let's look a little closer at it now. Density is a property of a material. It's the mass divided by the volume. Okay, we usually use this Greek letter rho for density, and it's equal to the mass of the object divided by the volume. Okay? Now, the density of some material or some mass is going to depend on pressure and temperature. But in general, when we keep temperatures and pressures from changing too much, the density of solids and liquids depends upon the type of material. Okay? So for example, steel has always about the same density. Okay? And water has always about the same density. For things that are made up of a conglomeration of different materials, the density is different for different areas within the object, right? So one example might be your body, okay? Your body's made up of all kinds of different materials, and there's a range of densities of these materials, right? You have bones in your body, and they have a density of around 2,000 kilograms per cubic meter, okay? And you have muscle attached to these bones, right? You have muscles like this attached to the bones. And those muscles have a density of around 1,060 kilograms per meter cubed, right? But then there's some body fat in there, right? Maybe some body fat right here that's in there, and the body fat has a density of something more like 920 kilograms per meter cubed, right? And then there's blood, and blood has a density just a little bit higher than water, right? So for an object like your body, with this varying density inside of the volume, right? The volume is well defined. It's everything inside the skin, right? The total mass of the object divided by the total volume will give you the average density of the object, okay? So yes, your body is made up of a whole bunch of different things that all have varying masses, but the average density of your body is your total mass divided by the total volume. So as I mentioned before, liquids can only be compressed by the tiniest of amounts. So liquids, for our purposes here in classical mechanics considerations, are generally effectively uniform in density based on the fluid, okay? So water has a density of about 1,000 kilograms per cubic meter, okay? And oil has a density of less than water. It's usually around 800 kilograms per meter cubed. Okay? In both of these cases, this density is uniform. Okay? This density is for all pure water. This density is for some given kind of oil. And all of that oil is going to have this same density. Okay? Gases, on the other hand, readily change their volume. So the same mass of a given gas will have a different density based on the volume that it's occupying. Okay? And in practice, often we take advantage of the fact that gases will readily change their volume by manipulating the density of a gas, by manipulating the temperature and pressure of a gas. Okay? And by doing that, we can force it to try to create a bigger volume when we make it hotter, okay, and when we increase the pressure. And we take advantage of these these types of properties for things like combustion engines and things like that. Okay? But in general, the density of our gas is going to be based on the volume that it's occupying, because it'll readily occupy whatever volume we give it. Okay? So now let's introduce the concept of pressure. The molecules of a fluid are bouncing around with a speed that's based on their temperature. Okay? So let's take my water molecule again. In the water, the molecule isn't just sitting there, it's flying around with some speed. Okay? So in water, I have all these molecules, and they're all flying around with speeds in various directions. Okay? So when there's some surface up against the water, these molecules bump into this surface. Okay? So for example, this guy right here, it's going to fly in, it's going to hit this surface, and it's going to bounce off. Okay? When this happens, there's a change in the molecule's momentum, right? It was going this way, and then it goes out this way. That's a change in the momentum. Okay? But recall from the impulse momentum theorem that if the momentum of the molecule changes, there must be a force applied to the molecule for some amount of time, right? Delta P equals Ft. Right? That was our impulse momentum theorem. And this force that's applied is applied by the surface that the molecule is bumping into, right? But then remember Newton's third law. And when we consider that, then the molecule is applying the same force to the surface, right? It's an interaction between the molecule and the surface. And so when the surface applies a force like this to the molecule applies a force like this to the surface. Okay? This interaction of the molecule bumping off the surface is happening repeatedly all the time. So there ends up being this kind of constant force on this surface. Okay? It's happening over and over again from a whole bunch of different molecules, all bumping into this surface all the time. Okay? So we end up with some net force on the object. But you can see this process is basically happening for any little area that we look at on this surface, right? And we can describe this by kind of just thinking about the rate that it's happening, or the amount that it's happening per area. You can see if I considered the total force of all the molecules bumping off just this portion, that would be less than if I considered the total force of all the molecules bumping off this whole portion, right? So to describe this, we have a concept called pressure. Pressure, I'm going to use a capital P here, is equal to dF dA. Okay? It's a force per unit area. Okay? But pressure is a scalar. Okay? It's dF perpendicular. All right? The pressure is always normal to that little piece of area. So if we have a glass of water, the water is applying a pressure to the glass, to this wall of the glass, and that pressure is normal to the wall of the glass, okay? And to the bottom, that pressure is normal. And to this side, that pressure is normal, okay? It's not a force pointed in this direction, right? It's a force normal to the surface. And all fluids do this. All fluids have a pressure based on the circumstances that they're in, okay? So the pressure of the water on the glass is dependent upon, first, what fluid is in here, okay? In this case, if we say water, it's dependent upon the properties of water. It's also dependent upon the depth of the glass, okay? And then if we squeeze it or press on the bottom of it, it's dependent upon that kind of a force that we applied to the top. If we had it this nice and sealed on the top and we squeezed it from this way, we would increase the pressure as well. Okay? But the pressure applies to all the surfaces that the fluid is touching. All right? So now let's go a little further and look at how pressure depends upon depth. Okay? If you've ever dived down underwater in the ocean or in a deep pool or something like that, you've probably felt the effects of changing pressure. In particular, you can generally feel it in your ears, right? Pressure changes with depth in a fluid because of the weight of the fluid. So anytime we're dealing with enough fluid that its weight becomes important, we'll have to start dealing with changing pressure as our depth in the fluid changes, okay? So let's consider some fluid in equilibrium here, okay? And that is, for any piece of the fluid, there's no net force acting on it. It's just sitting here, okay? So if we look at a little box in the fluid here, this top area has some area A, and then this bottom surface has that same area A, okay? And then this thickness of our little box we'll call dy, okay? So it's going to have a force acting on the lower surface here from pressure, right? Pressure is going to act normal to the surface, just like it does to every other surface. So this little box, this little portion of the fluid that we're considering, it's going to have some pressure pushing up on the bottom. And if we call that pressure on the lower surface P, so lower surface P, then we can call the pressure on the upper surface P plus dP. Okay? And it's P, the pressure on the lower surface, plus some amount of change, right? No matter what this pressure is, we could describe it this way. We're just describing it in reference to P. Okay? So the little box has these two forces on it, but then it also has gravity acting on it, right? It has some mass, and it has mg pulling down on it. Okay? But what is the m for the box, right? M for the box is the density of the fluid times the volume of the box, right? We said before that density equals mass over volume. So if I take the density of the fluid and I multiply it by the mass if I take the density of the fluid and I multiply it by the volume of the little box, I'll get the mass of the fluid in the little box, okay? So if I do this, then this volume becomes the volume is A dy. And so the mass of the fluid is rho A dy. Okay? So now let's just apply Newton's second law using these properties, okay? So for Newton's second law, I just add up all the forces. We'll make up positive, all right? So in the positive direction, we have the force acting from pressure on the bottom surface, right? And that was P times A, okay? To get a force from pressure, I have to multiply it by the area that the pressure is acting on. And then pushing down from the top, we have the pressure on the top, P plus dP, again times A, okay? And then also pulling down, we have the force of gravity, right? The weight of the fluid here. And that's rho A G dy. Okay? And then if this is in equilibrium, if this little piece of fluid is going to have no net force on it, then the acceleration is 0, right? So the mass times the acceleration is 0. So this is Newton's second law. Okay? Then we can just do a little bit of algebra. We have a PA here, and we have a minus PA from this term here. Those are going to cancel. And so we're going to have A dP. We can bring this term to the other side and say that's, a minus A dP. And we can bring this term to the other side and say we have rho A G dy, right? And then that means, after the A's cancel, that dP equals minus rho g dy. Okay? And this tells us that pressure increases as the position goes down, right? So if dy is a little negative piece, it goes down, then the pressure goes up. Okay? And if we integrate this over a specific integral, okay, from P1 to P2 minus rho g dy from y1 to y2, then we get P2 minus P1 equals minus rho g y2 minus y1. So then we have a relationship with delta P, right? P2 minus P1 is delta P, and delta Y, right? But if we call this change in Y the depth, so if we go from the top down to some point, right? And this is Y2 and Y1, then this distance, Y2 minus Y1, we can just call that H, okay? We'll call that the depth H. And then we can call the pressure at the surface right here, the pressure right here at the surface of the fluid, we'll call that P naught, okay? Or P at zero depth. If we do that, then we can solve for P and we can see that the pressure at some given depth is P naught plus rho GH. And this is the equation that I want you to write down and remember for later use, okay? This one gives us the pressure of a fluid based on our depth in that fluid. P equals P naught plus rho GH. And this equation allows us to quantify the change in pressure that you feel as you dive deep down in water, okay? As you dive down, the pressure increases based on this equation right here, and it quickly goes far past the normal atmospheric pressure that your ears are used to, okay? Now, when we were doing this, remember that I did this integral. Right? That was part of our derivation. Now, when I did this, I pulled the density out of the integral, okay? By doing that, I'm saying that this density is not a function of y, okay? What I'm really saying is that this density is uniform. It's just some constant. So this derivation for this equation up here that tells us the pressure based on the depth in a fluid relies on the fluid having uniform density, okay? So this is really good for liquids because they have uniform density. But for something like the gas of the atmosphere, that is not uniform in density. So this calculation is a bit more complicated, but the same basic idea applies, okay? The pressure of the atmospheric gas is greater at sea level, but then as I go up in altitude, the pressure from atmospheric gas decreases, okay? As I reduce my depth in the atmosphere, the pressure decreases. Now, it doesn't follow this equation because the density of the gas is not uniform, okay? But it does follow the same basic idea where as I reduce my depth in the fluid, the pressure goes down, okay? The pressure applied by the fluid goes down. So this is why an airplane cabin needs to be pressurized. They fly high enough that the pressure of the atmosphere is really low outside the plane, and it would be harmful to people to sit in that low pressure, okay? So they pressurize the cabin so that you can be comfortable. Maybe freezing cold, but comfortable otherwise. Now, thinking about this and thinking about sitting in the bottom of a big sea of fluid is always very interesting to me. I think it's interesting to think about when we see things in the ocean. We see fish and corals different plants and all kinds of things, all kinds of life down in the bottom of the ocean. And it seems strange to us that they can just sit under the water, right? And they just breathe water. But really, they're just sitting in some big sea of fluid, right? And us sitting in the atmosphere, it's not really so different, is it? We're just sitting at the bottom of some sea of fluid as well. Now, our lungs are designed to breathe that fluid in the same way that a fish's gills are designed to breathe the water, right? Breathe the fluid that they're in. And obviously they don't interface well because the density of those fluids is vastly different, right? So our lungs can't operate underwater, obviously. But when we think about it, all of the life that we've seen, at least up to this point, is some biological thing just sitting in the bottom of a sea of fluid. I think that's interesting, the parallel between the two. But that takes us off topic a little bit. Let's get back on topic, okay? So let's look at our equation for pressure in a fluid of uniform density, okay? That's this guy right here. Note that if I increase the surface pressure, P naught, I increase the pressure everywhere for all H, right? So P goes up as P naught goes up, right? We can look at this just like we do our sanity checks for our problems, all right? This is called Pascal's principle, okay? Pressure applied to a fluid is transmitted undiminished to every part of the fluid and to the walls of the container. Okay? So, this is how something like a hydraulic lift works. So, in the case of a hydraulic lift, I have something here, and I have a nice seal, and I have kind of a plunger that can push down. And then over here, I have a much bigger kind of area that's sealed here. And I can apply a force here, and that increases the pressure, right? This thing has some area, and this force equals the area times the pressure, right? And then the pressure, when it increases everywhere in here, right? All of the fluid has an increase in pressure. And so the pressure that's on this surface right here is equal to the pressure that's on this surface right here, right? And pressure is, we'll call this one surface 1. So the pressure must be equal to F1 divided by A1, right? Pressure is always force per area. But it also must be equal to F2 over A2. But then that tells us that F1 equals A2 over A1 F2. And we can take advantage of the fact that the force is different because we modified the area that this pressure is applied to. And that allows us to take advantage of the fact that the pressure is the same everywhere within this fluid when we change it at one point. And that allows us to have things like hydraulic lifts. This is the way the brakes on your car work. It's the way the dentist chairs work. Okay? All of these things take advantage of the fact that as we increase the pressure on a fluid, the pressure is increased everywhere in the fluid, not just on the part that we push on. Okay? And this comes directly from the fact that our liquids are uncompressible. And again, we call this Pascal's principle. Pressure applied to a fluid is transmitted undiminished to every part of the fluid and to the walls of the container. So that concludes our lecture for today. In our next lecture, we'll continue looking at fluids and look at some new properties of fluids.